So, hi everyone. Today we are going to talk about the very important topic from inorganic chemistry, that is our CFT, crystal field theory. So, crystal field theory is considered to be one of the very important topic because it has a very good weightage in your competitive exams, right? Now, CFT is also a theory which explain about the formation of bonds between the metal and the ligand. Now, basically, if we say how this word crystal field theory came, so basically this theory जो था ना, crystal field theory, uh, basically it was originally applied to an ionic crystal. It was सबसे पहले it was applied to an ionic crystal. Why it was applied to explain the optical property, the optical behavior, you can say, basically the optical behavior. And that's why and that's why it is called crystal field theory. So basically it was applied to an ionic crystal, right? Before CFT we study about a theory, I hope you all remember, that was VBT, valence bond theory. Valence bond theory. This is the theory which we studied before the crystal field theory. Now, what's the difference between these two theories? If I talk about valence bond theory now, in valence bond theory, what we consider that the bond between the metal and the ligand. This bond is the covalent bond. This was my covalent bond which was formed by sharing the electron pair by the metals and the ligands. They used to share the electrons. There will be overlapping of the orbitals. Due to the overlapping of orbitals, there will be the formation of bonds, right? But there was a small problem in VBT. What was the problem? The major drawback of VBT was that it was unable to explain. It was unable to explain the color and the magnetic property and the magnetic property of compounds. That we all have studied that generally most of the coordination compounds are color compounds, right? Why they are colored? Second thing, if I talk about the magnetic behavior, some are showing diamagnetics, few shows the paramagnetic nature. Why there was the magnetic property? All this explanation VBT failed to give, right? So to overcome this drawback, we got to know about the new theory that is called as crystal field theory. Now, in crystal field theory, there are few important points. The very first point that we say, according to crystal field theory, the interaction the interaction between metal and ligand is purely electrostatic. Is purely electrostatic interaction. Matlab, CFT does not believe that the bond formed between the metal and ligand is covalent bond. According to CFT, we'll consider the bond to be ionic bond, right? And if there is wherever we have ionic bond, so there is a force of attraction that we all know, that force is called as electrostatic force of attraction, right? Second, here जो ligand होता है, the ligands are considered to be are considered as point charge. Basically, they are considered as point charge. What type of ligands? You can write anionic ligands basically. So ligands having negative charge. All the anionic ligands are considered to be point charge, and the the ligands which are neutral, for example ammonia, for example water, neutral ligands are considered are considered as dipole. These are considered as a dipole. Matlab, if I talk about let's say water is something like this, OHH. So we'll consider this is delta positive, and this is delta negative. You can take any other, like say I'm talking about ammonia. Nitrogen will have delta negative and 3 hydrogen will have delta positive. So for neutral ligands, we consider this thing as a dipole, right? And there will be the interaction between the negative end of this dipole and the positive part of the metals, because we all know that metals क्या होता है? Metals are the electropositive species, right? They are electropositive in nature. Now, if I talk about the ligands, ligands क्या करेगा? Ligands will actually surround the metal. So metals are always present in the center of the universe. Let's say I have a metal present over here. So ligand क्या करेगा? Ligand will try to surround this metal from all the direction, right? It will try to approach the metal from all the direction. Now, whenever it will try to approach, whenever it tries to approach, what will happen? It will approach in such a way that the repulsion between these two ligand and ligand will be minimum. So to minimize this repulsion, they occupy a certain geometry, right? They will occupy a certain distance. So here we say that the ligand will approach or they will surround the metal in such a way that the repulsion between the ligands should be minimum. Why there will be repulsion? I hope you know that ligands are electron pair donors. So these are negative charges. So like charges repel each other. So to minimize repulsion, they will occupy a certain geometry. Now, so whenever ligand approaches metal, there will be two types of force. If I talk about force, so there are two types of interaction. There are two types of interaction between metal and ligands. There are two types of interaction. What are those two types of interaction? So the very first type of interaction is that is called as force of attraction. There will be force of attraction. So force of attraction किसके बीच में होगा? So there is a force of attraction which takes place between, force of attraction is between the nucleus of the metal, between the nucleus of the metal and the negative charge of the ligand. So basically we know that ligands क्या होता है? Ligands will have the negative charge. Metals will have nucleus. Nucleus are always positive charge. So there will be force of attraction between the positively charged nucleus and the negatively charged ligand. So both will attract each other. This is called as force of attraction. Similarly, there will be one more force which will act here, that is called as force of repulsion. Force of repulsion. So there will be a repulsive force and this repulsive force will act किसके बीच में? This will act between the filled d orbitals of metals. We have studied that metals have filled d orbital and they have empty s orbital, right? So with that s orbital, it generally makes bond, sigma bond, and then metal have a filled orbital by which it donates. So sometimes it makes a back bonding. I hope you remember that is the bond between the metal carbonyl. So we get the synergic bonding, right? There was a back donation. How this back donation? Carbonyl was having empty pi star, metal has the filled d orbital. So from d orbital, metal again it can donate back to the ligands on the empty orbital of ligand. That we call it as back bonding, right? So force of repulsion will be between the filled d orbital of metals and the negative charge of, and we can say negative charge of ligand. Either we can say negative charge or we can also say for neutral ligands there will be lone pair. That will lone pair of ligands, because if I talk about water, ammonia and all, they are the lone pair donors, right? So lone pairs and metal ka electrons or the negative charge ligand and the metal ka d orbital electrons, they will repel each other and they will try to balance the force of attraction and force of repulsion, and they will try to accommodate different types of geometry. Now, as we are talking about the metals d orbital, so if I talk about the d orbital of metal, so I can say basically point number 5, metals have five d orbitals. Okay, it has 5 different types of d orbitals, and all this orbital have same energy, have same energy. Their energy is same. That's why it is called as degenerate. These are called as degenerate orbital. Degenerate matlab hota hai the orbitals which have the same energy. So right now when the metal is in free state, when the metal is in free ionic state, at that case all the 5 d orbitals of the metal, they will have equal amount of energy. So what are the different types of d orbitals that we have? first we have this type. This is called as, let's say this is my x-axis, this is my y-axis. So this is called as dxy. Second, same diagram we can draw with different axes. Let's say this is my y-axis, this is my z-axis. So I'll say d yz orbital. And third, if I draw something like this between z orbital, z axis and x axis, this is called as dzx. Now this orbitals जो है, in this orbitals what will happen, this orbital will contains the electron, metal का d electrons will be present in this orbitals, right? And as these orbitals are present in between the axis, because this is the axis and the orbitals are present here, so electron density is between the axis. That's why these three types of d orbitals are called as non-axial orbital. These are also called as non-axial orbital. Why non-axial orbital? Because the electron density or the lobes of the d orbitals, they are present in between the axis. If they are present in between the axis, these are called as non-axial orbital. I hope this is clear. And this non-axial d orbitals are also called as T2g orbitals. These are also called as T2g orbitals. With this, there are two more types of d orbitals. What are those? So we have one more d orbital, which is something like this. Let's say this is my y-axis, this is my x-axis. So this is called as dx square minus y square. Now you can see in this orbital, the lobes are on the axis, right? These are on the axis. So these are called as axial orbital. Similarly, we have one more d orbital again. The last one is a 3D orbital. It's very difficult to draw it in a plane. I'll try to explain you like this. So let's say this is my z-axis. Okay, this is my x-axis. And there will be a ring. There will be a ring which will be present on xy plane, something like this. Yes, sir. So here you have electron density on this xy ring and then on the z-axis. So this orbital is called as dz square. So in these two orbitals, you can see the maximum number of electron density are along the axis. That's why these are called as axial orbitals. These are known as axial orbitals. Why? Because the electron densities are present along the axis, and this type of orbitals are also called as EG orbitals. Correct? Okay. Now, see what will happen in this case. According to CFT, what we consider in CFT, if you remember here, the interaction between the metal and ligand is purely electrostatic. Matlab, right now, what will happen? There is a metal. Let's say here is the metal present. Okay. Here is the ligand. Ligand is present at infinite distance right now. The distance between a metal and ligand is infinite. So ligand will have some symmetrical field, right? It will have its ligand field basically like this. This is the symmetrical ligand field of the ligand, and metal is also symmetrical. This metal right now, it is symmetrical. Now what will happen? The ligand will slowly approach towards the metal. Right now, there is no distortion, there is no interaction between the metal and the ligand. As soon as the ligand will try to approach the metal, what will happen? The metal will have the nucleus. Nucleus is the positively charged, ligand is the negatively charged. So the nucleus of the metal will pull the negative charge of the ligand towards itself, right? When this nucleus of this metal pulls the ligand, what will happen? There will be distortion taking place. Due to distortion, जो metal it was symmetrical, now it will become unsymmetrical as soon as the metal will approach here. Now, when it becomes unsymmetrical, what will happen? There will be splitting. How splitting? Because right now metal has 5 d orbitals which are degenerate. Matlab they have same energy. As the metal approaches as the ligand approaches the metal, due to force of repulsion, few d orbitals will feel more amount of repulsion and their energy will increase. Few d orbital will feel comparatively less repulsion and their energy will decrease. So we can say there will be a distortion taking place, right? So how this distortion will take place? Let's take an example for octahedral field, right? So I'll take an example for octahedral complex, yeah, octahedral field, right? Example, octahedral field looks something like this, ML6, right? and here you will have some charge. Metal will have some charges, right? So in this case, how do we see? In this case, what we'll see, we'll say that there is a metal. Okay, let's say I'll draw the metal. Just a second, sorry. So here I have a metal, and here I have a field like this. It looks like an octahedral. Okay. So here, 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 and here I have ligands. Here I have ligands present. All this case. Always याद रखना ligand जो होता है ना, ligand always approaches from the axis. From the axis. Ligand will always approach the metal through the axis, right, along the axis. Now we have studied, we have two different sets of d orbital, few orbitals, three d orbitals which are non-axials and two d orbitals which are axial. Matlab if electron comes from the axis, if it is coming from the axis and the metal ka d orbital which is whose lobes is present on the axis, they will feel more repulsion. If they will feel more repulsion right now, जो degeneracy था, the degeneracy will get breakdown. So right now, if I want to explain how it will look like, देखो. So this was the d orbital of the metal. 1, 2, 3, 4. Let me draw nicely. Sorry. 1, 2, 3, 4. So these are the 5d orbital. मतलब d x y, d y z, d z x, d x square minus y square, and d z square. Right. Now this all 5d orbital, they have the same energy. So ये कहाँ पे present है? This we say that these are the orbitals in free ion, free metal ion state में it is present like this. ठीक है? Right now ligand is at infinity. As the ligand will try to approach metal, what will happen? Slowly, slowly metal will feel the repulsion and it will feel the attraction. As the repulsion and attraction is very less, what will happen? All these 5d orbitals, they will feel equal amount of repulsion and all 5d orbitals energy will increase. They will have, still they will have same energy. Here energy increases, right? In this way energy increases. So as the ligand approaches closer and closer to the metal, so due to more amount of repulsion, all 5d electrons energy will comparatively increase. Now when the ligand approaches the metal field में if ligand approaches, now the interaction will be more. How the interaction will be more? The ligand when it approach metals towards the axis, and those d orbitals whose lobes are present on the axis, they will feel more repulsion, so their energy will increase and few energy will decrease. This is the zero energy. This zero energy is called as barycenter. This is called as barycenter. Which two orbitals will have more energy? Whose lobes are present along the axis? कौन कौन सा होता है? d x square minus y square and d z square. Their energy will increase. And the three d orbitals whose lobes are present in between the axis, like dxy, dyz, dzx, their energy will comparatively decrease. And this is how this is the average energy. This is called as average energy of d orbital. कहाँ पे? This is in spherical field. ठीक है? In a spherical field, this will be the average energy. Now as the ligand enters the metal field, so there will be more repulsion. Due to repulsion, ये जो degeneracy था, the degeneracy got broke down, and due to breaking in degeneracy, 3d or 2d orbitals their energy increased and 3d orbitals energy decreased. Right? This distance is called as delta naught. This delta naught O represents octahedral complex. Right? This is called as delta naught, and this difference is this is equal to 3 by 5 delta naught, and this lower one is equal to minus of 2 by 5 delta naught. Now if I add 3 by 5 and 2 by 5, I'll get the answer as 0. It should come to be 0. Matlab overall change in the energy of d orbital should be 0. There should not be overall change. Matlab this two orbital energy increase हुआ, right? The amount of energy increase for this two orbital, similar amount of energy should decrease for other three orbitals, so that the net energy change should be equal to 0. And when you find the energy, between energy difference between these two set, that energy is called as crystal field splitting energy or crystal fields stabilizing energy, right? So if I want to find CFSE value, I can say CFSE is equal to number of electrons in T2G set multiplied by 2 by 5 minus of 2 by 5 plus number of electrons in EG set multiplied by 3 by 5, right? Along with this, I'll add small amount of XP. What is XP? XP is called as pairing energy. This is called as pairing energy. What is a pairing energy? Pairing energy is the amount of energy required to pair electrons. Right? If I want to make the electron to be paired, so there are few amount of energy required. Again, this energy is very small. So usually when we calculate the CFSE value, we neglect the pairing energy. Okay? In this way, we can calculate what to say CFSE value. So basically, if we talk about ligands, if you remember in VBT, we have talked that we have two types of ligands, right? I'll just write in a very small thing. So ligands, we have learned that I have two types of ligand. One was strong field ligand, another one was weak field ligand. What is a strong field ligand? But a strong field ligand will be those ligands in which the splitting will be more. If splitting will be more, then delta naught will increase. Delta naught will be very high. If delta naught will be very high, then electron मतलब यहाँ पे देखो, if this gap is very large, right? This gap is very large. So can electron goes from T2G orbital to EG orbital easily? No, because the energy gap is large. So that's why in this case pairing will take place. So I can say in this case delta naught should be greater than the pairing energy. And which ligands are called as weak field ligand? The ligands which decreases the energy gap between them. Matlab I can say that if delta naught is less than the pairing energy, those ligands are called as weak field ligands. I hope this is clear. So what type of questions you will get? Let's do one question and then we can wrap up, right? So example, if they have given you some complex like cobalt H2O6, let's say 3 plus. Now, how to do this one? First, we have central metal, that is cobalt. You can write the electronic configuration of cobalt, that is 4s2 3d7. Oxidation state of cobalt is 3 plus. So remove 3 electrons, 2 from S, 1 from D. So it will become 3d6. Right? Now, arrange the electron. I'm just writing the electron in two sets. We have here 3 and here we have 2. T2G and EG, right? I have to fill 6 electrons. Now, to fill the 6 electrons, I have to identify whether the water is a strong field ligand or a weak field ligand. Now, beta, ये बात याद रखना that water in cobalt 3 plus is considered to be a strong field ligand. This is a strong field ligand. If the ligand is strong field, then what do you think? This energy gap will be very large. So electrons cannot jump to the higher state. Electrons, it cannot go to the EG orbital. So right now we have to do the pairing. How many electrons I have to fill? 6 electrons. So I will fill electrons as 1, 2, 3, 4, 5, 6. This is how I will fill the electrons, right? Now, what they can ask you? देखो, एक तो they can ask you the geometry. Let's say they are asking you about the geometry. What is the geometry of this one? 6 है, so it will be sp3 d2, ठीक है? और d2 sp3 basically. अच्छा, to find geometry we have to go with VBT. ठीक है? Okay, I'll explain you about the geometry also. It will be d2 sp3 basically. Strong field ligand है. I'll write 1, 2, 3, 4, 5, 6. 2 d orbitals are empty. 1s, 3p, right? So this is 3d, 4s, 4p. So geometry is going to be d2sp3. This is going to be d2sp3. This is my hybridization. ठीक है? If hybridization is d2sp3, geometry क्या आएगा? Geometry will be octahedral geometry. इसके साथ they can ask you number of unpaired electron. How many unpaired electrons I have? I have 0 unpaired electron. If I ask about magnetic moment, हम कैसे निकालते हैं? n into n plus 2 का root over n is number of unpaired electrons. So magnetic moment is going to be 0. If there are no unpaired electrons, this type of complex are called as diamagnetic complex. These are called as diamagnetic complex. Okay. Now sometimes they can ask you this is a high spin or low spin. You can see all the electrons are paired up, so that's why this is called as low spin complex. Okay. This is an inner sphere or outer sphere because right now for hybridization this is using inner d orbital. That's why it is also called as inner sphere complex. Yeah, inner sphere orbital भी बोल सकते हैं. Correct? So similarly, I'll give you a question which you can try at home. So try to find all these values for let's say Mn, NH3, 6, 2 plus. Now you have to decide whether ammonia is a strong field or weak field ligand. If you remember, to classify ligand as strong field and weak field, we have studied about a series called as spectrochemical series. So just use that series, try to find the ammonia ka this thing and then find all the value. Sorry, we can also find the CFSE value. So I'll give you an example how to calculate CFSE for the above one. If I want to calculate CFSE value, I can say how many electrons are there? 2, 4, 6, right? 6 into number of electrons in T2G. So what I have to multiply? I have to multiply by minus 2 by 5. And in EG, I have 0 electron. So it will be 0. So how many electrons will be? Minus 12 by 5. This is going to be my CFSE value. I hope this is clear. So let's do this much for today. In next class, we'll see how this crystal field basically splitting takes place in tetrahedral as well as square planar complex. Okay? Sure. So that's all for today. Thank you so much.